Every time you run a piece of code, there's this secret conversation going on. It's not just you telling the computer what to do. Nope. It's this whole hidden dialogue with its own private language and its own set of rules. So today, let's kind of pull back the curtain and listen in on that conversation. We're going to decode two of the most fundamental ideas, types and declarations. So think about it. When you write a word like position or a symbol like a plus sign, how does the computer have any idea what you're talking about? It's not just reading text, right? It's trying to find the meaning behind it all. And that's the real mystery we're going to unravel together. How does our code translate our ideas into a language that a computer can actually understand? Okay, let's start with just one simple line of code. At a glance, yeah, it looks like a basic math formula. But to a computer, it's like a sentence in a brand new language it's never seen before. And before it can even dream of doing the calculation, it has to understand the grammar, the vocabulary. Every single part of this, every word, every symbol, has a specific meaning that has to be figured out first. So let's zoom in on the names in our code, words like position and rate. Before the computer can do anything with them, it has to be properly introduced. I mean, think about it like meeting someone new, right? You need to learn their name and maybe a little something about them. Well, in the world of programming, that formal introduction, that's called a declaration.
A declaration is really just a formal handshake with the compiler. You're basically saying, hey, compiler, I'd like to introduce you to a new name I'm going to be using. It's called position. And here's what kind of thing it is. This first step, it doesn't give it a value just yet. It just lets the compiler know it exists and what to call it.
And this brings up a really important and sometimes kind of tricky distinction, declaring something versus defining it. When we say int I, that's the declaration. We're introducing I and telling the compiler it's an integer. But when we say I equals 1, that's the definition. That's when we actually give I its value. It's kind of like the difference between telling a friend about a box and then actually putting something inside of it. All right, so when we declare something, we're giving it a name, but we're also giving it a type. So what's the deal with a type? What is it really, and why is it so important? Honestly, the best way to think about a type is as a rule book for that specific piece of data. So if you declare rate as a floating point number, its rulebook says, okay, I can hold decimals and you can use me in multiplication. But that same rulebook says, no way, you can't ask me what my third letter is. That makes no sense. The type literally defines what's possible and what's not. And these rules, they're incredibly useful. They basically turn the compiler into the super vigilant proofreader that can catch silly mistakes before they ever become a real problem. But types do more than just enforce the rules. They also tell the compiler exactly how much memory it needs to set aside for each piece of data. Yeah, you can picture the computer's memory as this vast warehouse. When you declare an integer, the compiler goes and finds a little for-byte container just for that number. It's the perfect size, just sitting there on the shelf waiting for a value. But what if you need to store a number with a decimal? Well, a floating point number needs a bit more room to be precise, right? So the compiler grabs a bigger 8-byte container instead. By telling it the type, you're essentially giving the compiler the exact blueprint for the storage box it needs to build. And types aren't just for simple things, like single numbers. They can get way more complex. You can build these intricate nested structures, almost like a set of Russian nesting dolls. This type here is an array that contains two smaller arrays, and each one of those holds 3 integers. It's a really elegant way to group related data together, like, say, the color values for a single pixel on your screen. So wait a second. The compiler's keeping track of all these names and all their types and where they all live in memory. How in the world does it remember all that? Well, it turns out it has a secret weapon, a special little notebook. And this notebook is called the symbol table. It's basically the compiler's brain. Think of it like a super detailed contact list for every single name in your program. For every variable you create, there's an entry in the symbol table that lists its name, its type, and its exact address in memory. So here's a really simple version of what that table might look like for our little line of code. It's just a clean, organized chart. You can see each name, its type, they're all floats, and its address in memory. And you'll notice how the addresses are just stacked one after the other. As each variable gets declared, it just gets the next available spot. Okay, so how does this all come together? Well, as the compiler reads your code, it breaks it down into these little pieces called tokens. And whenever it bumps into a name, like rate, it immediately goes and looks it up in the symbol table. And the table tells the compiler everything it needs to know. Rate is a float, and here's where you can find its value. The symbol table is the key. It's what unlocks the meaning of your code. All right, we've gone pretty deep here. Declarations, types, this whole symbol table thing. But why does any of this actually matter when you're just trying to get your code to work? Well, it's all about having a clearer, more intentional conversation with the computer. At the end of the day, here's what it all boils down to. Declaring a variable isn't just about making a placeholder. It's a powerful statement of your intent. You're telling the computer exactly what this piece of data represents, what it can do, what it can't do. And being that clear, that precise, that's the foundation of writing good, reliable, and efficient code. You know, there's a real elegance to how these systems are designed. It's all about this delicate balance between power and simplicity, this art of creating these beautiful, efficient models. And what's really cool is that as a programmer, you're not just using these systems, you're taking part in that design every single time you write a line of code. This whole conversation between types and declarations, it's just one of the many secret chats happening inside your code all the time. So next time you sit down to program, maybe just take a moment and appreciate that hidden world just beneath the surface, that quiet symphony of logic and language that's busy turning your thoughts into a digital reality.